Well, ask yourself, who in AB would not be in there? Remember, the FNs converge point-wise. So for a fixed epsilon, just weight long enough. And there's some n. Right? There's some n that puts you within epsilon at a particular x. So no x escapes. Every x in AB is in some ON. Admittedly, it might be for huge n, but at least it's in. We're going to infinity, so we're going to capture it, right? Okay, now, I claim the sets ON are open. Why is that? You see that ON is a pre-image of the set is a pre-image of this set. And what's the definition of a continuous function? Oh, sorry, this is not the pre-image. It's this. It's f minus fn inverse of the integral of epsilon. So this is really a cumbersome notation. This is continuous, assume. This is continuous, assume. The difference of continuous functions is continuous. The pre-image of an open set under a continuous function. In fact, that's the definition of continuity. The pre-image of every open set is open. That function is continuous. This is an open set. This is a continuous function whose pre-image of this set under that continuous function is being taken, and that defines ON. So the ONs are open. Again, because I assume f is continuous, and we know the fn's are continuous. This is why in Dini's weak converse to the uniform limit of continuous functions is continuous. This Dini's theorem is a weak converse to that. You have to go out and assume that f is continuous, so that you can now say the difference of two continuous functions is still continuous, and then the pre-image under that is open, right? Okay. So we use the continuity of everybody. The monotonicity now becomes important. You see these? As the union grows, everybody's stacked together, right? If you cut it off at some level, everybody prior is already in a particular ON, right? Now, if the ONs are open sets and they cover this compact interval, what can we say? There's a finite subcup if the set's open, right? But they're all stacked up, aren't they? So what can we do? This is just like division. Just cross it off. The only one that counts is the one with the highest index, because he's got everybody else below him already inside it, right? Okay. So apparently there's an n sub k. And once you're at n sub k, the difference f minus fn is okay for any point in AB is less than a pre-assigned epsilon, right? I claim if n is greater than this n sub k, then the difference doesn't have to be absolute, because we know this is the big one. I only needed, and this is for all x in AB, I only needed to go up to the index nk to capture everybody in AB. So I claim this condition works for everybody in AB now, right? We fixed epsilon in advance. And as long as we're past nk, that means we're at least at onk and beyond, right? We don't have to actually go any further. But if you pick an n bigger than nk, it's guaranteed that this difference here is less than epsilon. But that's uniform convergence, isn't it? If you fix epsilon and you find an n such that once you get past it, the difference between the function and one of the approximates is less than that fixed epsilon for any x in the domain of interest, that's uniform convergence. Hence Dini's conclusion is the convergence is uniform. Okay. That's a famous theorem from the 1880s or so. Okay. We wanted to establish the condition, the Cauchy condition, the Cauchy criterion for uniform convergence. And we can say that if the usual, if Fn is a sequence of functions defined on some common domain, could be all real axes or not. So they're all defined in the same place. So it makes sense to talk about convergence. If Fn is defined on E here, and then Fn converges uniformly to F if and only if there exists, for all epsilon greater than 0, there exists an n of epsilon such that whenever n and m are greater than that n of epsilon, it follows that the absolute difference of Fn of x minus Fm of x is less than epsilon for all x in. So that's a statement of the theorem. I think I might have written something like that down on the sheet there. So this is an if and only if, which means we have two directions. Suppose it converges uniformly. So we're given uniform convergence. How can we establish then this condition? This is the criterion of Cauchy's criterion. This is good practice, and this is the sort of thing they do in grad school. This one isn't too, well, heck, this is a grad course about. We should be doing it. How do you get that condition out of what you have? Well, what's it mean to converge uniformly here? It means that this implies there exists, well, let's fix epsilon first. Always a good idea to fix an epsilon. And there exists an n of epsilon such that whenever n is greater than n of epsilon, it is true that Fn of x minus f of x is less than epsilon for all x in E. Okay, that's just a recap or rehash of uniform convergence on E. If we can put an m there, we'll be done, right? How can we sneak an m in there? First, we'll have to sneak it in out there too. How can we sneak it in there? You're always creative.
Obviously, plus and minus.
How about this? How about a lot of these proofs rely on the triangle? So Fn, let me suppress the x. Fn minus Fn is equal to Fn minus F plus F. Oh, is that what you were saying?
Yeah.
Yeah, right, absolutely. And then by the triangle inequality, that's less than or equal to Fn minus F plus, and we'll just turn, no, we don't have to turn that on. Okay, all right? most they observe is the old plus or minus trick, and then the triangle angle, which seems to motivate a lot of proofs.
And choosing an again large enough so that each of those actually beyond the first of epsilon.
So there's an n sub epsilon that allows you to go out to make these less than epsilon. So really, let's, we can say epsilon prime is equal to epsilon over 2, and then you go past epsilon prime, and each one of these is less than epsilon over 2. So the sum of those, namely epsilon, dominates this, which dominates that, for any x in E, so that's that direction. Right? I think that was what we said.